Hey everyone, I am Ms. Hu, your physics teacher. In this video, you'll be learning about how a mirage is formed and how sound curves both in the daytime as well as night. These are actually natural phenomena involving total internal reflection of light and sound. Now, this video is actually an extract from the video on my complete lesson on total internal reflection. So if you'd like to understand a bit more about total internal reflection, please watch that video. I'll put the link in the description below. I've decided to extract this part of the video into a separate one because I have received some questions about how a mirage is formed and also how sound curves. So now let's begin first with how a mirage is formed. Now, what is a mirage? So a mirage is like an optical illusion where we will perceive something to be on the ground when it's not really there. You hear a lot of stories about this in the deserts where people have reported seeing water on the ground, but when you get there, there's no water. In fact, the stories of the Flying Dutchman, go read up about it, is believed to be mirages. So they're not actually ghost ships. It's just that there's a ship somewhere else properly sailing on water, but perceived to be floating and flying above the surface of the water. Now, a mirage can only happen on a very hot day. And why is this? So let's look at this diagram. We've got someone here in the desert and a cloud in the sky. So the mirage can only happen when the surface is very hot. That means it's got a low specific heat capacity, or it's a good heat conductor, so it tends to absorb heat. Some of you may even have observed mirages on a road. For example, if you're in a car on a very hot day and you're looking straight ahead, sometimes you can see what appears to be a puddle of water in front of you on the road, but when you get there, there's actually no water. So this also works because the surface of the road is very hot, very low specific heat capacity. So how does a mirage actually occur? Like I said, this only happens when the surface where we're observing the mirage on has a low specific heat capacity or tends to get hot very, very quickly. Because it gets hot so easily, it causes the air just above that surface to be very hot as well. And as we move further away from the hot surface, of course the temperature gets cooler. So to help you visualize this, I've put layers of different temperature air here. So red is representing very hot air, and as it goes up, the air is cooling down, so the cool air I've represented as blue. Now before we go into the light rays, some of you will be arguing, but wait a minute, doesn't hot air rise? We know that hot air has lower density and it should rise, which means that the cooler air should sink. And yes, you are right. But in this case, why is it the other way? It is because of the very hot surface. So imagine that this sand here is acting like a heater. It's very hot. It's continuously heating up the air above it. So when the hot air rises, it's moving further away from the hot surface, so it tends to cool down. So by the time it gets up, it's cool. It's trying to sink again, but when it sinks, it gets heated up by the heat source again, and so on and so forth. So guess that's convection current, but we're not here to talk about convection. If you want to know more, go watch my videos on convection. For now, let's just understand that in this case, although hot air is supposed to rise, and it does, the air above the sand is much hotter simply because it's continuously getting heated by the very hot ground. Now, in order to be able to observe objects, remember that the light ray must enter our eyes. So let's say we have a light ray reflected off the cloud and it's going to try to enter the observer's eyes. In hot air, the air particles are further apart from each other compared to colder air. Because the colder air particles are closer together, we'll find that light tends to travel more slowly in colder air and travels much more quickly in hotter air. So let's have a light ray coming from a point on the cloud, like so. Now before we move on, just to clarify about these layers of air, I've drawn the layers of air here just to help you visualize what's happening with the light rays. In reality, we don't have layers of air like this, like, oh, all this is one temperature, next is all one temperature. No, in reality, it is a gradient of decreasing temperature. But if I were to draw gradients, I can't draw the ray paths. So that's why in this case, I've used the layers here just to help you visualize what's happening between the different temperatures of air. So remember that in reality, this is not how it actually looks like in real life. It is actually a gradient of temperature. But for now, let's use these layers to help us understand. When light is traveling from the cloud towards the eye of the observer, light ray is traveling from cooler air to warmer air. That means that when it travels down, it encounters air that has a higher temperature than the layer of air before it. So because it's getting warmer, this means that the light ray is traveling faster. So the light ray is traveling faster, it's going to refract away from normal. So here's the normal line, and you can see I've drawn a light ray where it is refracted further away from normal compared to the incident ray. When this light ray reaches the next temperature gradient, again, it's going to refract away from normal. And this process keeps going until the angle of incidence is greater than the critical angle. So that means that at one point, you'll find that the light ray will undergo total internal reflection. So when the light ray enters the observer's eye at this point, the observer will see a cloud along this path. And obviously, the cloud is not going to be floating in the middle of the air. You're going to see the cloud formed on the surface of the ground like this. And because clouds are basically, water that's floating in the air, when we observe the cloud on the ground, it looks like water on the ground. That's why when mirages are observed in the desert or on the road, we tend to see puddles of water, because those puddles of water are actually the image of the clouds that we see on the ground like this. So that's how a mirage is formed. Now, besides light, sound can also undergo total internal reflection. Let's take a look at what happens in this situation. Starting first with sound in daytime. Now let's say we've got these two young lovers who are trying to recreate the iconic scene from Say Anything. So we've got this young man who's got a boombox and he's trying to play the sound for his beautiful girlfriend to hear. Again, I'm going to put the different layers of the different temperatures of air to help us visualize what happens to the sound. Sound travels at different speeds in different temperatures. So for hotter air, because there's more energy, sound tends to travel faster compared to colder air where there's less energy. So when it's higher temperature, more energy, the air particles can move faster, therefore transferring sound more quickly. Compared to colder air, which is moving a lot slower, so the transfer of energy is also much slower. This time, the sound is coming from the bottom where the radio is. So I'm going to draw an arrow to represent the direction of the sound wave. So when the sound is traveling from the bottom layer to a higher layer, it's traveling from warmer to cooler air. So remember, sound travels faster in warmer air, slower in cooler air. That means the sound is going to be traveling more slowly. So when it travels slower, it's going to refract towards normal. This keeps happening at every layer. As you can see again, the sound is refracting towards normal, enabling the sound to easily reach his girlfriend who is on a higher floor. So yes, whatever love song he's playing for her, she's going to be able to hear it clearly. Now, of course, one thing we do know about sound is that it's omnidirectional. That means sound doesn't travel in one direction. It actually spreads out because sound is parabolic in shape. But basically, even if the sound was omnidirectional, let's say if I'm drawing sound waves like this, because sound waves tend to travel upwards, you'll find that the sound waves tend to curve upwards towards the listener. By the way, she'll be able to hear the sounds from the boombox clearly, and even if he's speaking, she may be able to hear him quite clearly. But if she were to respond, he probably can't hear her. Why? Because, as we can see in the daytime, sound tends to travel upwards. That means that if she were to speak, the sound of her voice will tend to travel upwards, away from him and not towards him. So if she says something, he's going to be like, "What? I can't hear you. What? Speak louder." Some of you may have even experienced this phenomenon where your friends might be on a higher floor and you're on the ground floor. So when you're speaking, they can hear you. But if they try to shout back, you'll be like, "Dude, I can't hear you. Can you speak louder?" So it's not that your friends are not speaking loud enough. It's because of physics. The sound tends to travel upwards in the daytime. Now, what about sound in the nighttime? So now let's say this guy decides to visit his girlfriend at night, again with his boombox. And in terms of the temperatures of air, finally, the balance of the temperature gradient is restored. As we have already learned, we know that hot air rises, and in this case, yes, the warm air will be on top, and the cooler air will be at the bottom. Why? Because at night, the ground is much cooler. It's not going to heat up the ground, so the hot air gets to stay on top. So in this case, when the sound is traveling from the boom box, it's going to be traveling through the cooler air first before reaching the warmer air. Let's start with one arrow to represent the sound wave. So sound is traveling from cooler to warmer air. And as we know, sound travels faster in warmer air, which means it's going to refract away from normal. And at this point, it could refract in such a way that the incident angle is greater than the critical angle, causing the sound to totally internally reflect. Now, some of you may say, hey, of course this is cheating. The angle here is already so big. So let's start with a smaller incident angle this time. You'll find that the sound wave is still going to refract away from normal because the temperature of the layer of air above it is warmer. And as it keeps going up, it's going to refract further away from normal until the incident angle is greater than the critical angle, causing the sound wave to undergo total internal reflection. And yes, we do know that sound is omnidirectional, but because of the way the sound waves are behaving, you're going to find that the sound wave ends up curving downwards. So it's going to be very difficult for the young lady to hear the music that her boyfriend is playing from this boombox. So if you ever want to recreate this iconic scene from the movie, Say Anything, if the person that you're targeting is on a higher floor, then you've got to do this in the daytime, not at night. So the comparison between these two situations of the sound in the daytime and sound at night explains a lot of real-life phenomena. For example, if you live in a high-rise, you'll tend to hear the sounds from traffic much more clearly in the daytime compared to at night. But at night, sometimes you still hear a lot of sound because at night, sound can travel a further distance due to total internal reflection. And now we've finally come to an end to this video about total internal reflection. If you'd like to know how to solve some questions or go through some worked examples with regards to total internal reflection, I'll put that in another video because I think this video has been long enough already for you to sit through. If you found this video to be educational and helpful, please click like, do comment about how this video has helped you, and of course subscribe for more free physics lessons. Do check out my YouTube channel for videos on other topics which you might find helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. For notes, quizzes, and syllabus updates, check out my website at physicsrocks.com. Happy studying!